As I said before, if we say MJO theories, that means there is more than one theory, which is not necessarily good news, right? Nonetheless, they have all some things in common, because the way theories evolve, obviously you have observations, you build a hypothesis, you get more observations to test the hypothesis, and if things are confirmed again and again, you make it a theory, and then you have to go from there. And obviously a lot of the data allude to some of the basic processes which are used by people to explain MJOs. Just for completion, I'll also include MISOs here, Monsoon Intra-Seasonal Oscillations. This nice figure I took from a book on tropical climate dynamics by Tim Lee and Su. I think Pang Chi Su, HSU. I'm not saying it right, of course, sorry. So this is showing standard deviation of the 20 to 80 day filtered precipitation anomalies shaded in millimeter per day, and the precipitation propagation vector during northern summer in May to October and northern winter in December to April. The data used here is from CMAP rainfall data. So you can see that the boreal summer season ISOs have genesis around the same place. There is convection being generated in the western Indian Ocean pretty much throughout the year, and there is eastward propagation, and then there is a northward detouring of the interseasonal oscillation, and there is also some that propagate from the northwestern Pacific Ocean across the South China Sea into the Bay of Bengal. And there are different time scales involved. For example, the northeastward propagating ones are 30 to 60 days, and northwestward propagating ones are more at 10 to 20 days, quasi-biennial time scale, quasi-bi-weekly time scales, and so on. And this is our favorite MJO that we are talking about right now during December to April. Typically we look at November to April or October to April. People talk about May to September, October to April, or May to October, November to April, and so on. So here you can see that the precipitation is spread along the Indian ITCZ and the SPCZ here, whereas in this season the ITCZ moves north here, but over the Indian Ocean it gets split. You get what is called often the tropical convergence zone over the monsoon domain, and you get the marine ITCZ where the sea surface temperatures remain pretty warm throughout the year. So there are many MJOs which actually go south and across, as I said before, and some go across near the equator, some get stalled, and some slow down, some seem to jump, and so on and so forth. So it is often referred to as MJO diversity, but by Bin Wang, for example, but I won't go into that. This is again a summary. It's called a tri-mode theory, I think, by Bin Wang. That's from his paper. I'm going to use that as a schematic to explain generally what are the common things among most of the theories. There are various names like wave CISC. So CISC is the convective instability of the second kind, which includes dynamic uplift. First kind is just warming and instability, static instability kind of thing. But we talked about this convergence and the divergence at the top level with dry phase ahead, Rossby waves behind, Kelvin waves ahead, and here it is boundary layer moisture convergence. So K low, R low are the Kelvin and Rossby waves, and there is the boundary layer, and there is the upper layer quadrupole structure that we typically talk about with the opposite phase pressure centers here. So low here, high there, divergence here, convergence here. So almost all the theories include these surface heat exchange. So let's say evaporation, latent heat flux, sensible heat flux, mostly latent. They talk about moisture convergence and then lifting of the moisture into the free troposphere, but often the differences are in whether the convergence is happening in the frictional boundary layer, or if it is facilitated by waves and advecting the moisture gradients rather than evaporating it and lifting it from the surface. And they all have these waves somehow included included in the theories, and so the names can be moisture, recharge, discharge, moisture mode theory, wave CISC, and so on. But as I said, if there are multiple theories, that just means that there is still no consensus on exactly what happens. But most of them also include ideas for why it propagates eastward. So if you have easterlies ahead of it and westerlies behind it, then these tend to enhance, let's make sure. They tend to slow down the climatological winds and create warming ahead. There are also changes in cloudiness, radiation, flux involved, whereas here the westerlies enhance the background winds and cool the SSTs, so then convection moves forward. There are also ideas of wind evaporation, SST feedbacks, and so on and so forth. This is just a schematic again from one of Bin Wang's paper that talks about dynamic moisture mode and just the so-called moisture mode. And as we said before, this diabatic heating source in the tropics produce waves, but the question is, are the waves then able to affect moisture convergence? In the moisture mode theory, there is a role for the waves. So basically, it also comes down to how sea surface temperatures themselves may be affecting the MJOs. It is clear in some models that when the model is coupled to the ocean, then the MJOs are better simulated, they are stronger, they propagate with the more realistic speed and so on. But the question is, how does sea surface temperature actually affect the MJOs? So you can think of basic state moist static energy, vertical instability, lifting moisture through the boundary layer, and then moisture feedback to convective heating. And in the dynamic mode, you also have free atmospheric wave dynamics affecting convergence, geopotential variability, and boundary layer dynamics, and so on. So I'm not going into details, but just giving you a sense that people invoke various contributions based on observations, and different aspects are emphasized by different people. So you can read more on review articles by Chidong Zhang and Kunio Yanayama, and by Madden and Julian themselves, or books like Peter Webster or Tim Lee and Su. Okay. Quickly moving on to the monsoon intra-seasonal oscillations. One of the theories that was there for a long time was by Xianan Jiang, Tim Lee, and Bin Wang. This is a schematic from Bin Wang's review paper again. So we are looking at X and Y. So the monsoon intra-seasonal oscillations, as we said here, propagate northward from the tropical, or around 5 south, even across the equator. So the question is, of course, where the energy comes from and why do they propagate northward? Again, this is an open question. There are multiple theories. This was schematically explained this way, where you have, once the monsoon dynamics begins to happen, cross equatorial flow, ocean land contrast, and so on, you have easterly shear. So you have low level winds that are westerly, upper level winds that are easterly. So if you have easterlies, you curl your fingers, you get a horizontal vorticity, and in that case you create also subsidence, moisture convergence near the surface, so you have vertical velocity. Vertical velocity begins to tilt the horizontal vorticity, and then essentially create tilting differently ahead of the convection and behind convection. So you end up with this meridional gradient in the vertical velocity. So you have vertical velocity downward here, upward here, of course, maximum in the convection center, and then upward and downward. So you have upward tilting of the vorticity here, downward tilting of the vorticity here. So this paper argued for a very strong role for the vertical shear as the main driver that couples the baroclinic and barotropic modes and creates conditions favorable for convection to organize ahead of the existing convection center and give you forward or northward propagation. Some little more details are added now to the same paper by Baosheng Li, which is coming out soon, where they say that it's not just the vertical shear, it's actually the meridional gradient of the vertical velocity that actually tilts the vorticity. So the vorticity is lifted up in the convection center, and behind it, where you have anticyclonic vorticity, so you curl your fingers this way, you have vorticity tilting happening this way, and ahead of the convection you have cyclonic vorticity, and you have vorticity tilting going the other way. And this is argued to be very critical because in the models, the models that do the vertical shear but do not do the proper vorticity tilting do not produce the good amount of rain and good northward propagation and so on. So similar ideas but different details. This matters because even in MJO there is a westward tilting of the convection, which you can see here, kind of the southward tilting, if you will. So again, theories are still being formulated and they are not confirmed yet in terms of the exact theories that can explain consistently the northward propagation, let alone both eastward and northward propagation, and why the season is split around May and then again in November. Of course, must have something to do with the movement of the sun and the ITCZ, because the ITCZ is the riding factor in driving this. So there is a basic question of what selects this intraseasonal timescale in the first place. Diurnal cycle and so on can explain weather timescales with feedbacks, moisture feedbacks and condensation heating feedbacks and so on. And ocean memory can explain the climate timescales, seasons, because sun moves back and forth on seasonal timescales. And then you have this bridge from weather timescales to climate timescales, which are clearly present, which gives us predictability, which is our focus here. But exactly what is the scale selection involved is not so clear. So within that you have to explain MJOs and MISOs, which have many theories, but not there is no consensus on what is the best theory or what is a unified theory yet.